Okay, everybody, we're going to do some notes, second set of notes for Unit 4 here. So the title of these notes is actually kind of long, so here we go. It's chemical symbols and formulas of elements and compounds. Chemical symbols and formulas of elements and compounds. So remember, way back at the beginning when we talked about matter, you can split matter into two categories. You can split it into pure substances and mixtures. And the pure substances side is elements and compounds, okay? That's anything you can write a chemical symbol for or a formula for, okay? And so we're going to talk about how those symbols and formulas are written depending on the type of substance. Okay, so to start off, we're going to talk about elements. Okay, so most elements exist in nature as billions of atoms forming a solid chunk of material. Okay, so when you look at a piece of iron, for example, billions and billions and billions and billions of atoms make up that piece of iron as a big chunk, okay? But some elements exist as gases made up of single atoms or as solids, liquids, or gases made of pairs of atoms floating independently of each other, okay? So when you look at a gas, for example, our air is mostly nitrogen and oxygen. Those two elements, nitrogen and oxygen, don't exist as single atoms floating around. They exist as little pairs that are bonded to each other, and then those pairs are floating around each other, okay? And there's liquids and solids that have that arrangement as well. Okay, and so we have some words for these. All right, first off, monatomic. Monatomic. Hopefully you guys already know that mono means one, okay? So monatomic literally means single atoms, okay? These are elements that exist as single atoms, and they are the noble gases, which if you aren't familiar with that yet, we did do that color-coded periodic table way back in the fall. Noble gases are group 18, so helium all the way down to radon. Those are the noble gases, and they exist as single atoms floating around by themselves. They're the only elements that exist that way. All right, diatomic. Di means two. It doesn't mean two or more, it means two. So diatomic literally means two atoms. Two atoms, okay? And so these are going to be solids, liquids, or gases that exist as pairs of atoms, okay? So pairs of atoms, atoms paired with themselves, okay? So here's a little trick to remember which ones are diatomic. All the gens and all the enes are diatomic. So any element name that ends in gen, hydrogen, nitrogen, oxygen, those are diatomic. But the enes as well, fluorine, chlorine, bromine. I know we pronounce it differently, but it still ends in ine, iodine, okay? All of those are going to be diatomic as well. Okay, so now let's talk about how we write symbols for these elements. For most elements, I'm going to put that on a different line, sorry. For most elements, we simply write the symbol of the element. So you just look for it on the periodic table, and you just write its symbol. So iron would be Fe, okay? Copper, Cu. Carbon, C. So you just look for it on the periodic table, write its symbol. Pretty simple. All right. For diatomic elements, we write the symbol with a subscript of 2. Okay. This is to show they exist in pairs. All right, so here's all of the diatomic elements. Hydrogen, it's going to be H2. Okay. Oxygen, O2. Now, when they're in a compound, they might not necessarily have a 2 there. Okay, like water is H2O, it's not H2O2. We don't put a 2 next to oxygen every time. But when they're pure, when you say hydrogen, that is H2. If you say oxygen, that is O2. If you say carbon monoxide, there's oxygen in there, but it's not the word oxygen, right? It's carbon monoxide. So that is a compound. It is not going to follow this 2 business, okay? So only in their pure form. All right, there's one more gen. Nitrogen is going to be N2. All right, then we get into our enes. Fluorine, which is F2. Chlorine, which is Cl2. Bromine, Br2. And iodine, I2. Now you might be thinking, well, what about acetine? Because it's in that same group, it ends in ene. Sure, you can add that if you want. Acetine is a super rare element. We're not going to be working with it a lot, so you won't be seeing that symbol. But those are the 7 that you're going to see fairly regularly that you want to know are diatomic. All right, that ends our elements for us. So we're going to move on to compounds now. Okay, there are many types of compounds, including ionic. We've learned about ionic compounds, covalent compounds, acids, bases, and organic compounds. Okay. We're going to talk about each of these individually here and how we're going to write those formulas. Okay, so ionic compounds, they have to contain a metal and a nonmetal. Okay, there are some exceptions to that that have polyatomic ions, but I will always give you those formulas. So they contain a metal and a nonmetal. Their names do not have prefixes. Okay, so remember, we've named these already. They just name that cation and then the anion. Okay, and they will end with "ide." So all of the ionic compounds we've been naming are going to end in "ide." Okay, now there are some compounds that don't follow these rules, and they're more complex, but I will always give you their formulas. If it's a simple ionic compound, I will expect you to take its name and make its formula. But if it's a more complex one with polyatomic ions, I will give you the formula. Covalent compounds. These contain 2 nonmetals. Okay, so we've been working with diatomic, or not diatomic, binary covalent compounds that have two nonmetals, okay, their names do have prefixes, always. There's always at least one prefix in the name, carbon monoxide, for example, okay? So mono would be that prefix. So their names do have prefixes and still end with "ide." So IDE is not really going to tell you what kind of compound you have. You have to look in the name and see if there's prefixes. All right, acids. We haven't really talked about acids yet. We'll get into a unit of acids and bases pretty soon. But the name of an acid always contains the word acid. Okay, so hydrochloric acid, nitric acid, sulfuric acid, things like that. Their chemical formulas generally start with hydrogen and will be given to you. So you won't have to create the formula for an acid in this unit, okay? You're just going to be given the formulas. All right, bases. Most bases we will use contain, whoops, typing too fast for my own good here. Contain hydroxide. Sorry, I'll scroll up so you can see this, okay? Most bases we will use contain hydroxide, which is OH. Okay, hydroxide kind of tells you that backwards, right? Hydrogen and oxygen, hydroxide, okay? In the name and in the formula. So you'll be looking for the word hydroxide, or you'll be looking for OH in the chemical formula to know that it's a base. You will be given the formulas of bases. So again, we're not going to ask you to reproduce the formula of a base, not in this unit. And then organic compounds. Organic compounds. The term organic, we've talked about it before, but we'll just review it real quick, means containing carbon. Okay. Organic compounds are made primarily of carbon and hydrogen, and sometimes other elements. So these are going to be compounds that are a little more complex, that have 3 or more elements in them, and we will give you those formulas. You'll be given those formulas as well. So in this unit, you don't have to, like, I don't have, if I tell you propane, I don't expect you to know the formula for propane, okay, or isopropanol or things like that. So those types of things, I will give you their chemical formulas. But elements, you're going to have to write down a chemical formula just by seeing the word, okay? So you'll have to know which ones get a 2 and which ones are just a symbol. And then ionic and covalent compounds that we've been working with already throughout the year, you're going to have to be able to translate their names into formulas as well. All right. So let's just do a little bit of a refresher on formulas. All compounds have a chemical formula. Okay, all compounds have a chemical formula with more than one element. Okay, so if it's a chemical formula like O2, that is a formula because it has a letter and a number, but it's not a compound because it doesn't have more than one element. It's an element, diatomic element, okay? All right, with more than one element, and subscripts, sorry, I had to find my place, telling us how many of each element are in the compound. Okay, so all compounds have a chemical formula. We're going to just really quickly refresh how to figure those chemical formulas out. Okay, so you have this in a previous part of your notes, but we're going to do this again. Okay, so you must know how to determine formulas of ionic and covalent compounds using their names. So let's just go through them one more time. All right. For ionic, you're going to use the charges. Use the charges to create the formula. Okay. Now, refreshing. Use the charges to create the formula. So let's just go through some examples. Sodium sulfide. Okay. On one of your periodic tables, I had asked you at one point to write down the charges that those atoms would form when they become ions. Okay. So what you do is you find sodium. Find sodium on that periodic table, and you'll see its symbol is Na. And you're going to see that if you followed my directions before, it has a charge of 1+ because it's in that first group. Group 1 is always going to form a 1+ ion. Group 2 is always going to form a 2+ ion. The yellow elements, those transition metals in the middle, we're going to skip those. They're strange, okay? Aluminum will always form a 3+ ion. Those are our always. Now, sometimes we're going to be working with some of those transition metals, and I will tell you the charge and the name using a Roman numeral. Working backwards from the other side of the periodic table, the noble gases are stable. They are always going to have a 0 charge. They don't form compounds. But fluorine's group 17, they always form a -1 ion. They always form a -1 ion. Group 16, oxygen's group, that's going to form a -2. And group 15, nitrogen's group, is going to form -3. So we find sodium, it's in group 1, and we figure out it's a +1 because of that. Sulfide is the element sulfur. And if we look at its group number, it's group 16, which is always going to be a 2-. Okay, so those are the charges that we need to work with when we form this compound formula. Okay, now you don't necessarily need to write these ions out, but I think it can help you when you're forming your formulas. Okay, so these two don't balance each other. A +1 does not balance a -2. Now, if you remember, and if you're handwriting these notes, you should be able to draw this. We did a little trick called the switcheroo. We take the number from sodium's charge and we bring it down here to be a subscript for sulfur. Not the plus, but the number 1. And we don't have to write ones when we have subscripts, so we don't have to worry about that one. Then we do the same thing for sulfur. The number part of sulfur's charge is going to come down here and be a subscript for sodium. Okay, so when we write this formula, we're going to get Na, the subscript 2, and then S with a subscript of 1, but we don't write ones. Okay, so Na2S is the formula for sodium sulfide. Sodium is a +1. We need 2 of those to balance a -2 charge from sulfur. So that's our formula. Okay, let's do another example. Calcium oxide. Okay, well, you look for calcium on the periodic table. Its symbol is Ca, and you're going to see that its charge, because it's in group 2, is 2+. Then you find oxide. Well, oxide isn't on the periodic table per se. Oxide is oxygen. Well, O, when it becomes an ion, if you look at its group, again, write those charges up at the top. O is going to be a 2-. Now, if you notice on this one, the 2+ and the 2-, they do balance each other. So we don't have to do the switcheroo thing. We get to just squeeze the letters together, get rid of those charges, and our formula is CaO. Okay? Remember, when you write a chemical formula, there are no charges in the formula. We use the charges to make the formula, but that's it. All right, let's do one more example here. Okay, iron 3 bromide. Okay, iron 3 bromide. So when you look at the periodic table, you find iron, and its symbol is Fe, and it's in the center of the table. okay? Remember, the center of the table are transition metals. They have lots of different possible charges, so we don't have a really easy way to see their charge by looking at the periodic table. We look at the periodic table to find the symbol of iron, and then we look back at the name. The name has a Roman numeral in it, and that Roman numeral is 3. So that means that our charge for the iron is 3+. Then we look at the periodic table again, find bromine. Bromine is in a column that has a regular charge, and the charge of that column is 1-. All right, now we do our little switcheroo. The number for the iron's charge, not the positive, but the 3, comes down here as a subscript for bromine. The number for the bromine, the 1, comes down here as a subscript for iron. We don't have to write ones. So Fe1, that's implied, Br3 is the formula for this compound, okay? Hopefully that's a good refresher. Please, please, please ask me for help if you're not remembering this stuff. Okay, covalent. Covalent compounds. Use the prefixes in the name to write the formula. Okay, all right, here's some examples. Carbon dioxide. Well, what's a prefix, you guys? This right here, di, that is a prefix. Carbon doesn't have one. Carbon's just the name of an element. So because carbon doesn't have one, we know that there's only one carbon. Dioxide means 2 oxygens, so O2. Okay, all right, let's do another one. Dinitrogen tetroxide. Okay, so again, what are the prefixes? Well, dinitrogen. Nitrogen is an element. We have to recognize our elements here. It makes it a little bit harder, okay? So dinitrogen means that this is a prefix, di. Tetroxide, okay? Oxide is an element. It's oxygen. So tetra is our prefix, okay? Now, remember, you have all these prefixes written in your notes somewhere. If you don't, then you should probably go back and write them again. See our previous notes on covalent compounds, okay? But dinitrogen means 2 nitrogens, so that's N2. Tetroxide, tetra is like Tetris. It means 4. Okay, each piece in Tetris is made of 4 little blocks. Okay, so tetroxide means 4 oxygens. So we do O4. We're not doing switcheroos on this. The name literally tells you how many of each thing are in the compound. Okay, all right, that is a refresher on ionic and covalent compounds. Remember, we will be giving you the acid, base, and organic compound formulas throughout this unit. We'll learn a little bit more about those later, and you'll be able to create their formulas later. But right now, those will be given to you, okay? All right, thanks for tuning in, and we will see you in class. Again, please, please, please let us know if you have any questions.